Tonight, we're going to talk about a signal from space that no instrument glitch, no natural source, and no 50 years of searching has been able to account for. A signal so precisely shaped, arriving at exactly the right frequency, lasting exactly the right duration, that the astronomer who found it had no explanation for what sent it. It shouldn't exist. Not according to anything we know about stars, gas clouds, pulsars, black holes, or any natural process the universe is supposed to produce. In the decades since, astronomers have found more of them. Signals from billions of light years away, releasing more energy in a millisecond than our sun produces in 3 days. And the question of what is sending them has quietly become one of the most unsettling problems in modern astronomy. By the end of tonight, you're going to understand exactly what these signals are and why some of the most careful scientists in the world still can't fully explain them. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The story starts at a radio telescope called Big Ear, run by Ohio State University, sitting in a field outside Delaware, Ohio. It wasn't a famous instrument. It wasn't glamorous. It was a huge, flat structure of aluminum mesh spread across several acres of ground, built to catch radio waves instead of visible light. Radio telescopes work differently from the telescopes most people picture. They don't collect images. They collect radio waves, the same kind of electromagnetic radiation used for broadcasting and communication. The difference is where the waves come from, arriving from deep space instead of from a transmitter tower. Stars, galaxies, gas clouds, and a long list of natural cosmic processes all produce radio emissions. By tuning in to specific frequencies, astronomers can learn things about the universe that ordinary optical telescopes simply can't show them. Big Ear was part of a project called SETI, the Search for Extraterrestrial Intelligence. The idea behind SETI is simple to state and staggeringly difficult to execute. If another technological civilization exists somewhere out there, and if it uses radio waves the way we do, then somewhere in the sky there might be a signal we could actually detect. Not a message meant for us, specifically. Just leakage. The accidental radio noise any advanced technology tends to produce. Or possibly a deliberate broadcast, sent out in the hope that someone, somewhere, might be listening. On the night of August 15th, 1977, Big Ear was doing exactly what it did every night. Scanning a fixed strip of sky, letting Earth's rotation slowly sweep that strip past the telescope's field of view. A computer recorded the signal strength at each of 50 individual channels, each one representing a slightly different frequency. Nobody was sitting at the telescope, watching in real time. The data was being printed onto paper, long continuous sheets covered in columns of numbers. It would sit there until someone came in to review it. That someone was Jerry Eman, an astronomer volunteering with the project. A few days after the recording, he sat down with the printout and started scanning through the numbers, looking for anything unusual in the noise. Most of what he saw was exactly what he expected. Background, static. Faint, inconsistent readings that didn't rise above a handful of units on the scale the telescope used to measure signal intensity. And then he reached one particular sequence and stopped. The signal strength scale Big Ear used ran from 0 up through the numbers 1 through 9. After that, it continued into the letters of the alphabet, with A representing 10, B representing 11, and so on. A normal background reading might show up as a 1 or a 2. Anything reaching 6 or 7 was already considered a strong signal. The sequence Eamon was looking at read 6, E, Q, U, J, 5. Translated into actual numbers, that's 6, 14, 26, 30, 19, 5. The signal had rocketed up from background noise to an intensity 30 times stronger than anything else recorded that night. Then it faded back down again, tracing a smooth curve across exactly 6 consecutive readings. That shape mattered enormously. Big Ear's receiver swept across the sky as the Earth rotated beneath it. That meant any real signal coming from a fixed point in space should rise gradually as the telescope's beam swung onto it, peak when it was centered directly on the source, and then fade gradually as the beam swung past. That is exactly what the data showed. A clean, symmetrical rise and fall, spread across about 72 seconds, which happened to be almost precisely the amount of time Big Ear's beam would spend crossing a single fixed point in the sky. In other words, the shape of the signal looked exactly like what a real, distant, stationary source would produce. Not a spike, not a stutter, a textbook profile. There was something else, and this part is where it gets genuinely strange. The signal appeared in only one of the telescope's 2 receiving channels. Big Ear had 2 horns, tuned slightly apart in frequency, both looking at nearly the same patch of sky at almost the same time. That was a basic way of filtering out interference. Real interference from something like a passing aircraft or a ground-based transmitter would usually show up in both. This signal showed up in only one, and its frequency was close to 1,420 megahertz. That's the hydrogen line, the natural frequency at which the most abundant element in the universe, hydrogen, emits radio energy when its electron flips its spin state. That frequency is special for a reason that has nothing to do with mysticism and everything to do with physics. It's fundamental, universal, and quiet under normal circumstances in the sky. For decades, radio astronomers and SETI researchers alike had flagged it as one of the most logical frequencies for an intentional signal. The theory was that any civilization studying the universe would eventually stumble onto the same physics we did and might choose that exact frequency as a kind of natural, universal channel. Eamon circled the sequence of characters on the printout in red ink, and in the margin wrote a single word, "Wow." The name stuck immediately, and it's been called the wow signal ever since. For decades, scientists have gone through nearly every conventional explanation available. One by one, they haven't held up. The first suspect in any anomalous radio detection is always human interference. A stray transmission from a military installation, a passing aircraft, a piece of equipment malfunctioning somewhere nearby. But the frequency band, around 1420 megahertz, is protected by international agreement, specifically because it's used for radio astronomy, meaning terrestrial transmitters are barred from broadcasting there. And even setting that aside, the signal's behavior didn't match interference. It showed the gradual rise and fall, consistent with a fixed astronomical source drifting through the telescope's beam, not the sudden on-off pattern typical of a nearby transmitter switching on. The next suspect was a satellite. Satellites do sometimes produce false detections in radio astronomy, since a spacecraft passing overhead can briefly mimic a distant signal. But satellites move. Their signals sweep across the sky at a rate determined by orbital mechanics. And that rate is well understood and easy to calculate. Researchers checked the timing and shape of the WOW signal against every satellite that could plausibly have been in the area that night. None of them matched. The profile fit a fixed point far outside the solar system, not a moving object in Earth orbit. A more creative explanation surfaced years later, in 2017. A researcher proposed that the signal might have come from a comet, or possibly a pair of comets, releasing a cloud of hydrogen gas as they passed through that part of the sky. The idea was that the natural hydrogen line emission from that gas cloud might have produced the reading. It was a clever idea, and for a while it generated real interest. But when other astronomers checked the details, the explanation ran into serious problems. The comets proposed for the theory weren't actually in the right position on the night of the observation. A known cometary hydrogen emission at that frequency is far too faint, by orders of magnitude, to have produced a signal 30 times above background noise. Astronomers who specialize in studying comets pushed back hard on the idea. They pointed out that hydrogen emission at that frequency had never been reliably detected from a comet before. They also pointed out that the comets in question were too far from the Sun and too inactive to be producing anything close to the amount of gas the theory required. Researchers have also considered whether the signal came from Earth itself. Maybe it was reflected off a piece of space debris, or bounced off the Moon, or produced by some kind of unusual atmospheric effect. Each of these ideas has been examined, and each one runs into the same wall. None of them naturally produces a signal that does all three things at once: rises and falls with the specific timing of Big Ear's beam pattern, appears in only one receiver horn, sits precisely on the hydrogen line. It's not that scientists believe the signal was artificial in origin, sent by another civilization. Almost none of the researchers who've studied it are willing to say that. For decades, no natural explanation proposed actually accounted for every detail of what was recorded. That was a very different and much more honest position for a scientist to hold than simply calling the case closed. That changed, at least partially, in 2024. A team led by astrobiologist Abel Mendez proposed a new natural explanation using archival data from the old Arecibo Observatory. It was an idea that hadn't been seriously considered before. Their idea involves a cold, otherwise invisible cloud of hydrogen gas sitting out in interstellar space, the kind that exists throughout the galaxy without ever being detected directly. Picture a sudden, powerful burst of radiation passing through a cloud like that. The burst could come from something like a magnetar, or another kind of extreme, flaring stellar remnant. That burst can stimulate the cloud into a brief, dramatic flash of its own hydrogen line emission. It would act like a naturally occurring maser for a matter of seconds. Mendez's team found several fainter signals in old Arecibo data with strikingly similar properties to the WOW signal. They argue this mechanism can account for its strength, its narrow frequency, and its complete failure to ever repeat. It's a genuinely compelling hypothesis. It's the most serious natural explanation the WOW signal has ever had. But it remains a hypothesis, not a settled conclusion. It hasn't been independently confirmed by observing the exact same event happen again. The broader scientific community is still in the process of testing it. If the WOW signal really did come from something out there in that patch of sky, a natural question follows almost immediately. Why has nobody ever seen it again? The patch of sky, the signal, came from lies in the constellation Sagittarius. It has been searched, repeatedly, by multiple teams using multiple instruments across more than 4 decades. In the 1980s, and again in the 1990s, radio astronomers pointed dedicated equipment at the same coordinates and listened. Nothing. In 2012, on the 35th anniversary of the original detection, the Arecibo Observatory in Puerto Rico was aimed at the same region as part of a public outreach project. Arecibo was, before its collapse in 2020, one of the most powerful radio telescopes ever built. This time, the project actually transmitted a message toward the target rather than only listening. Later searches used the Allen Telescope Array in California, a facility built specifically for SETI research. It scanned the same coordinates repeatedly across a wide range of frequencies, looking not just for the exact hydrogen line frequency, but for anything nearby that might represent a repeat or a related transmission. Still, nothing. There are a handful of possible explanations for that silence. None of them require abandoning either a natural or an artificial origin. The source might have been a one-time astrophysical event, a rare and brief natural flare of some kind that we don't yet fully understand. If so, it may simply never repeat, the same way a single lightning strike doesn't happen twice in exactly the same spot. Or the source was an intentional transmission from another civilization. If so, it's entirely possible it was a short, one-time broadcast, not a continuous beacon. That would be similar to how a lighthouse beam only illuminates a given ship for a moment as it rotates past, rather than shining on it constantly. There's also a more mundane possibility. Whatever produced the signal could still be out there, still transmitting, on a schedule that simply hasn't lined up with the relatively small number of hours astronomers have spent listening to that patch of sky since 1977. Radio astronomy, in the decades since, has focused enormous resources on scanning wide areas of sky for any signal at all. But pointing a large, sensitive instrument at one single, narrow target for extended, continuous stretches of time is expensive. Telescope time is limited and shared among thousands of competing research projects. It's entirely possible the WOW signal's source has transmitted again, more than once, in the years since. It simply wasn't caught because nobody happened to be listening at that exact moment. That's not a comfortable answer, but it's an honest one, and it's the same uncertainty that runs through nearly every unexplained signal that's come since. For 30 years after the WOW signal, it stood almost alone, a single, unexplained data point in an otherwise quiet field. Then, in 2007, an astrophysicist named Duncan Lorimer was going through archival data from the Parkes Observatory in Australia. The radio data had actually been recorded years earlier, in 2001, and largely set aside. Lorimer, working with a student, was searching that old data for pulsars. Pulsars are a completely different and well-understood type of object. Rapidly spinning neutron stars that sweep a beam of radio energy past Earth with the regularity of a lighthouse. Instead, buried in the data, they found something that didn't behave like a pulsar at all. A single, extraordinarily bright burst of radio energy, lasting only a few thousandths of a second, that appeared once and never repeated. It became known as the Lorimer burst. It turned out to be the first confirmed member of an entirely new category of cosmic phenomenon, one that's since been named the Fast Radio Burst, or FRB. What made the Lorimer burst so strange wasn't just its brevity. It was the sheer amount of energy packed into that brief flash. Astronomers estimated its distance using a property of the signal called dispersion, which measures how radio waves of different frequencies get slightly delayed as they pass through the ionized gas scattered throughout space. Based on its brightness and that estimated distance, the burst appeared to have originated far outside our own galaxy, from a source billions of light years away. For a signal to be detectable across that kind of distance and still register as one of the brightest radio events ever recorded, in a burst lasting only milliseconds, was extraordinary. It meant whatever produced it released more energy in that instant than our sun produces in an entire day, possibly longer. At first, many astronomers were skeptical that the burst was even real. Nothing quite like it had ever been documented before, so they suspected instrument error or terrestrial interference. But, over the following years, astronomers went back through archival data from other telescopes and specifically started searching for similar signals. More of them turned up. Dozens, then hundreds, then eventually thousands of fast radio bursts have now been catalogued. They come from all directions in the sky, at a range of distances. Most trace back to galaxies billions of light years away, though at least one confirmed source sits inside our own galaxy. Almost all of them share the same basic profile: an intense burst of radio energy lasting a few thousandths of a second, appearing once and never repeating from that exact location again. But a small number of them broke that pattern in a way that made the mystery considerably stranger. In 2016, astronomers using the Arecibo Observatory identified something that had never been seen before: a fast radio burst that repeated. The source, catalogued as FRB 121102, sent out multiple bursts from the exact same location in the sky, on separate occasions, over an extended period of observation. This mattered enormously. A one-time event, no matter how energetic, could plausibly be explained by something catastrophic and singular, a violent, destructive event that happens once and is over. A collision between two extremely dense stellar remnants, for example, or the collapse of a massive star into a black hole. Those kinds of events only happen once at a given location, because whatever produced them no longer exists afterward. A repeating source rules that category of explanation out immediately. Whatever was producing these bursts from that location was still there and still active. It was capable of generating multiple, separate, extraordinarily powerful events from the same point in space. Follow-up observations eventually pinned down the source's location precisely enough to identify the galaxy it lives in, a small, faint dwarf galaxy, roughly 3 billion light-years from Earth. The environment surrounding the source turned out to be as strange as the bursts themselves, an unusually dense, highly magnetized region of space. Since that first repeater was found, dozens more repeating fast radio burst sources have been identified. In 2020, one of them added a detail that genuinely surprised the astronomical community. That source, along with several others discovered since, began showing bursts on a detectable, semi-regular cycle. Active for a period of days, then falling silent for a period of weeks, before becoming active again. One particularly well-studied repeater showed an activity pattern with a period of roughly 16 days. Active for about 4 days, then quiet for about 12, over and over. The rhythm was consistent and predictable enough that astronomers could actually schedule observing time around it. A cyclical, periodic pattern like that points strongly toward an explanation involving orbital motion, some kind of two-body system. The bursts would only be produced or only escape in our direction at a specific point in an orbit. The leading candidate to explain most fast radio bursts, including many of the repeaters, is a class of object called a magnetar. A magnetar is a neutron star, the extraordinarily dense collapsed core left behind after a massive star runs out of fuel and explodes as a supernova. But it has a magnetic field so powerful it defies ordinary description. A magnetar's magnetic field can be a quadrillion times stronger than Earth's. That's strong enough that if one existed halfway between the Earth and the Moon, it could erase every credit card and hard drive on the planet. Magnetars are known to produce sudden, violent bursts of energy when their crust cracks under the strain of their own magnetic field. These events are called starquakes. In 2020, astronomers caught a magnetar inside our own galaxy in the act of producing a burst with properties strikingly similar to a fast radio burst. That gave the first direct evidence linking the two phenomena. That discovery was a genuine breakthrough. It strongly supports the idea that at least some, and possibly most, fast radio bursts originate from magnetars. But it hasn't closed the case entirely. The magnetar detected in our galaxy produced a burst thousands of times fainter than the bursts researchers have detected coming from other galaxies. It remains unclear whether ordinary magnetar activity, even at its most extreme, can fully account for the most powerful fast radio bursts ever recorded. The kind that briefly outshine an entire galaxy's worth of stars in radio light. For now, the honest scientific position is that magnetars almost certainly explain a significant portion of fast radio bursts. But the field hasn't reached the point where every single detected burst can be fully and confidently explained. That's especially true of the periodic repeaters, with their strange, clock-like activity cycles. In 2020, a project called Breakthrough Listen was running one of the largest, most systematic searches for artificial radio signals ever conducted. It used the Parkes Radio Telescope in Australia to observe more than 1,500 nearby stars. Dedicated computer algorithms worked through an enormous backlog of recorded data designed specifically to flag anything unusual. Buried in observations of Proxima Centauri, the closest star system to our own sun at just over 4 light-years away, one of those algorithms flagged something that made the team pause. It was a narrow radio signal, sitting at a frequency of 982 MHz. It drifted slightly in frequency over time, in a way consistent with the Doppler shift you'd expect from a source on a rotating or orbiting body. That's exactly the kind of drift real astronomical signals typically show. The signal appeared during observations pointed directly at Proxima Centauri and vanished during observations pointed away from it. That's the standard test radio astronomers use to distinguish a real astronomical source from local interference. It was given the designation BLC-1, short for Breakthrough Listen Candidate 1. For a period of months, before any public announcement was made, a small team worked quietly to figure out what it actually was. The frequency itself raised eyebrows immediately. 982 MHz sits within a range commonly used by human technology, close to bands associated with television and certain communications equipment. It's a range where naturally occurring astrophysical signals are not expected to appear. For a signal at that frequency to be genuinely coming from the direction of Proxima Centauri, and only from that direction, was exactly the profile SETI researchers have spent decades hoping to eventually catch. News of the signal eventually leaked to the press in late 2020 well before the research team had finished its own internal analysis. For a period of weeks, headlines around the world described a signal from our nearest star system that nobody could yet explain. When the full technical analysis was eventually published, the picture became more complicated, though not fully resolved. Researchers found that similar narrowband signals with comparable drift characteristics had, on rare occasions, shown up elsewhere in the telescope's data, even when it wasn't pointed at Proxima Centauri. That strongly suggested some kind of terrestrial source of interference, possibly from equipment somewhere on the observatory site itself, capable of intermittently producing a signal that mimicked the drift pattern of a genuine astronomical source. The leading explanation that emerged was that BLC-1 was very likely the result of interference from human-made electronics. Most plausibly, a mixing of multiple locally generated frequencies produced a signal that happened to drift in a way that resembled a real astrophysical source. That is the most probable explanation, and it's the one most researchers on the project now favor. But it's worth being precise about the current state of the case, because it's often reported inaccurately. The research team has not been able to identify the specific piece of equipment or the specific mechanism that would have produced this particular signal. They've shown that similar false signals can occur, and that this general category of explanation is far more likely, statistically, than an artificial signal from another civilization. But a fully confirmed, specific, reproducible source for BLC-1 itself has not been pinned down. The signal exists in an unusual middle ground, almost certainly explainable by mundane interference, but not yet definitively and specifically explained. That distinction matters, because it's the same distinction that runs through this entire field. Very rarely does a candidate signal get definitively confirmed as either alien or ordinary. Far more often, it slides slowly over months or years of analysis, from mysterious toward probably mundane, without ever quite arriving at complete certainty. To understand why scientists take signals like these seriously enough to spend careers chasing them down, it helps to understand the reasoning underneath the entire search. In 1961, an astronomer named Frank Drake proposed a way of thinking about the odds of detectable civilizations existing elsewhere in the galaxy. It came to be known as the Drake equation. It isn't a formula that spits out a precise answer. It's a way of breaking an impossibly large question into smaller, more specific pieces. Each one is a factor that could, in principle, eventually be estimated through observation. How many stars form each year in our galaxy? What fraction of those stars have planets? What fraction of those planets could support life? What fraction of those actually develop life? What fraction of that life develops intelligence? What fraction of intelligent life develops technology capable of sending a detectable signal into space? And finally, how long a civilization continues broadcasting such signals before falling silent? That could happen through extinction, or simply through moving on to communication methods we wouldn't recognize as signals at all. When Drake first proposed the equation, most of those variables were complete unknowns. Today, thanks to decades of exoplanet research, particularly from missions like Kepler and its successors, we actually have a reasonably good estimate for some of them. We now know that planets are extremely common. Most stars in the galaxy likely host at least one planet. A meaningful fraction of those planets sit in what astronomers call the habitable zone, the range of distance from a star where temperatures could allow liquid water to exist on a planet's surface. What remains almost entirely unknown is how often life actually emerges given the right conditions. Also unknown is how often it becomes complex and intelligent, and how long a technological civilization might survive and keep broadcasting once it exists. Those uncertainties are enormous. They're exactly what drives the tension underneath a related, much older puzzle called the Fermi paradox. It's named after physicist Enrico Fermi, who is said to have posed a simple, blunt question over lunch with colleagues in 1950. If the universe is as old as it is, and as vast as it is, and if intelligent civilizations should plausibly have arisen many times over billions of years, across hundreds of billions of galaxies, then where is everyone? Why has humanity, after decades of dedicated searching, found no confirmed signal, no confirmed visit, no unambiguous evidence of any kind? There's no shortage of proposed answers to that question. Maybe intelligent life is simply extraordinarily rare. Maybe technological civilizations tend to destroy themselves or stagnate before they're capable of interstellar communication. Or maybe we've simply barely begun to search, covering only a vanishingly small sliver of the sky for a vanishingly small sliver of time, using methods that assume other civilizations communicate the way we currently do. Every unexplained signal, from the WOW signal to BLC-1, sits directly inside that unresolved tension. That's exactly why each one draws so much attention the moment it's found, and exactly why so much caution goes into ruling out every conceivable mundane explanation before anyone is willing to call something a serious candidate. The tools available for this search have changed dramatically since Big Ear first printed out its long paper record in 1977. Big Ear itself could only monitor 50 channels at once, a narrow slice of the radio spectrum. Its data had to be reviewed by a human being flipping through printed pages. That's part of why the WOW signal wasn't even noticed until days after it happened. Modern radio telescopes and modern signal processing work on an entirely different scale. Breakthrough. Listen, the project that flagged BLC-1 is capable of monitoring billions of individual channels simultaneously across a wide range of frequencies, using computing power that didn't exist in any form in the 1970s. Its algorithms can process enormous volumes of data in near real time, flagging candidate signals automatically rather than relying entirely on a person scanning printouts by eye. The Allen Telescope Array was built specifically with SETI research in mind. It was designed from the outset to allow flexible, wide-field, long-duration monitoring of large numbers of target stars, rather than the kind of single narrow beam observations older instruments were limited to. And the next generation of radio astronomy is already under construction. The Square Kilometre Array is an international project combining thousands of individual antennas spread across sites in South Africa and Australia. Once complete, it's being built to become the most sensitive radio telescope network ever constructed, with a total collecting area covering roughly 1 square kilometre. That dramatically exceeds the sensitivity of any single instrument currently operating. When fully operational, an instrument with that level of sensitivity will be capable of detecting far weaker signals at far greater distances than anything currently possible. It will effectively expand the volume of space that can be meaningfully searched by an enormous factor. There's also been a shift in what researchers are actually looking for. Early SETI work focused almost entirely on searching for deliberate radio broadcasts, on the assumption that another civilization might be actively trying to communicate. Modern searches have broadened considerably, looking for what's now generally called a technosignature, any detectable sign of technology, intentional or not. That could include unintentional radio leakage, similar to the way Earth's own television and radar broadcasts have been leaking into space for the better part of a century. It could include unusual patterns of light from a star, potentially caused by a large artificial structure passing in front of it. It could include atmospheric chemistry on a distant planet that doesn't match what natural geological or biological processes alone would be expected to produce. And it increasingly includes exactly the kind of anomalous radio bursts this entire story has been built around: energetic, structured signals that don't yet have a fully confirmed natural explanation. These get catalogued, tracked, and revisited as better instruments and better analysis techniques become available. It would be easy to tell this story in a way that leans hard into mystery, skipping past the harder, more careful parts of how science actually works. That wouldn't be honest. It wouldn't match what the researchers who study these signals actually say in their published papers and in their public statements. The overwhelming majority of professional astronomers who work on fast radio bursts believe the vast majority of them originate from natural, if extreme, astrophysical processes, most likely involving magnetars and their extraordinarily powerful magnetic fields, even in cases where the precise mechanism isn't yet fully worked out. The overwhelming majority of researchers who examined BLC-1 believe it was very likely a form of terrestrial interference, even though the exact source was never definitively pinned down. That caution isn't the field failing to find an exciting answer. It's the field doing exactly what good science is supposed to do: default to the explanation that requires the fewest new assumptions. Only seriously entertain more extraordinary possibilities, once every ordinary one has been carefully, rigorously excluded. But caution cuts in both directions. This is the part of the story that rarely gets the same attention. Being appropriately skeptical of extraordinary explanations doesn't mean every mundane explanation offered so far has actually been confirmed. The comet hypothesis for the WOW signal was proposed, reviewed, and effectively rejected by the very specialists best positioned to evaluate it. The specific mechanism behind BLC-1 has never been definitively identified, only judged statistically more likely to be mundane than not. Some fraction of fast radio bursts, particularly the strangely periodic repeaters, still don't have a fully worked out physical explanation, even under the magnetar model that best explains the rest of the population. What's left, once you set aside the sensational framing and the dismissive framing both, is a smaller, quieter, more honest category of cases. Signals that are almost certainly natural, or almost certainly terrestrial interference, but that have not, as a matter of documented, published, scientific record, been fully and specifically nailed down. That's not the same thing as evidence of alien life. It's simply an accurate description of where the actual data currently stands. That's precisely why these particular signals keep coming back into the conversation, year after year, revisited by new instruments and new analysis, waiting for either a definitive natural answer or definitive evidence of a repeat that could finally be studied properly. The patch of sky the WOW signal came from has now been watched, on and off, for close to 50 years. Whatever happened there, that one August night in 1977, has never happened again in any observation anyone has published. Proxima Centauri continues to be one of the most closely monitored stars in the sky, precisely because of its proximity, and precisely because of BLC-1. Newer, more sensitive instruments regularly turn toward it, looking for any signal that might repeat, drift correctly, and hold up under the kind of scrutiny the original candidate ultimately couldn't fully survive. And the broader catalogue of fast radio bursts keeps growing, month after month. Newer instruments, purpose-built for this kind of detection, come online and begin scanning wider areas of sky with greater sensitivity than anything that came before them. Each new burst gets the same treatment. Its position gets checked against known objects. Its frequency drift gets analyzed. Its timing gets compared against known sources of interference, satellites, aircraft, ground-based equipment. Most of the time, that process ends in a reasonably confident, natural explanation. Occasionally, it doesn't. Then the signal gets added to a small, carefully maintained list of cases that remain open, revisited whenever new data or new analysis techniques become available. There's something worth appreciating in the sheer persistence this entire effort represents. Nobody involved in this research expects to stumble onto a definitive answer quickly or easily. The people who spend their careers scanning this data know, better than almost anyone, how many ordinary explanations there are for an extraordinary-looking signal. They know how rigorously each one has to be checked before any stronger claim can even be considered. And yet, the searching continues, telescope after telescope, star system after star system. The alternative, simply assuming there's nothing left to find, has never once been supported by the actual history of this field. Each new generation of instruments has found things the previous generation couldn't. Fast radio bursts didn't even exist as a known category until 2007. Magnetar bursts weren't linked to them until 2020. The next leap in sensitivity, arriving over the coming years as newer telescope arrays finish construction, will almost certainly turn up phenomena nobody has catalogued yet. Somewhere in that growing catalogue of anomalies sits, at minimum, physics we don't yet fully understand. Extreme magnetic fields behaving in ways current models can't completely predict. Exotic dying stars producing energy releases at scales that stretch the boundaries of known physics. Environments so violent and so strange that simply cataloguing them expands what we know is physically possible in this universe. And somewhere in that same catalogue, however small the odds, there remains an open, unresolved, and entirely legitimate scientific question: whether one or more of these signals might eventually turn out to be something else entirely. To understand why a telescope was even listening to that patch of sky in the first place, it helps to go back further, to the very beginning of organized efforts to search for signals from other civilizations. In 1960, an astronomer named Frank Drake carried out the first modern SETI experiment. He called it Project Ozma, named after the princess of a fictional, faraway land in a series of children's books. Using a radio telescope in West Virginia, Drake pointed the instrument at two nearby, sun-like stars, Tau Ceti and Epsilon Eridani. He listened for a period of weeks, hoping to catch some kind of artificial transmission. He found nothing conclusive. At one point, the equipment did register a brief, startling signal. After investigation, it turned out to be a passing military aircraft rather than anything from beyond the solar system. Project Ozma didn't detect an alien civilization, but it established something more important, a method, a working example of how to actually go looking. It used instruments built for entirely different purposes, repurposed for this one very specific question. Over the following decades, that basic method was repeated, refined, and scaled up dramatically at observatories across the world. Radio telescopes that were often built primarily for conventional astrophysics got turned towards SETI research during whatever spare observing time could be found. In 1974, researchers used the newly upgraded Arecibo radio telescope in Puerto Rico to do something slightly different, not listening, but transmitting. They beamed a structured, 3-minute radio message toward a cluster of stars called Messier 13, roughly 25,000 light-years away. It encoded basic information about our solar system, our biology, and our technology into a simple binary pattern. The message won't arrive at its destination for another 25,000 years. Even then, there's no guarantee it will reach a system with anyone capable of noticing it, let alone responding. It was less a serious attempt at contact and more a demonstration. A proof that the technology to send such a message existed, and a symbolic gesture marking the upgrade of one of the world's most capable telescopes. By the time Big Ear picked up its strange 72-second signal in 1977, this entire field already had almost 2 decades of history behind it. A slow, patient accumulation of null results, interrupted occasionally by a candidate signal that generated excitement before eventually being explained. In a small number of cases, one was never fully explained at all. The wow signal wasn't the only candidate that generated real excitement before eventually settling into an uncertain middle ground. In August of 1967, a graduate student named Jocelyn Bell Burnell was working with a radio telescope in England. She discovered an extraordinarily regular pulse of radio energy, repeating every 1.37 seconds with almost mechanical precision. For a brief period, the source was informally nicknamed LGM-1, short for Little Green Men, only half jokingly. Nothing known in nature at the time was expected to produce a signal that regular. The explanation, once worked out, turned out to be a spinning neutron star, a pulsar, sweeping a beam of radio energy past Earth with each rotation. That's the same basic mechanism that produces the light from a lighthouse. The discovery earned a Nobel Prize in physics, though notably not for Bell Burnell herself, a point of long-running controversy in the history of the field. Pulsars turned out to be common throughout the galaxy. Their extreme regularity, once understood, became one of the most useful natural clocks in all of astrophysics, used today for everything from testing Einstein's theory of general relativity to potentially serving as navigation beacons for future deep space missions. In 1998, Arecibo Observatory recorded another anomalous signal that briefly generated headlines, quickly nicknamed the Wow of the Year. It never received the same lasting attention as the original 1977 detection, and was eventually attributed to a combination of terrestrial interference and instrument artifacts. In 2016, a Russian observatory reported detecting an unusual signal from the direction of a sun-like star called HD 164595, roughly 94 light-years away. The signal generated a wave of international media coverage within days, with some outlets suggesting a possible artificial origin. The scientific team that first flagged it was considerably more cautious. They noted that it had not been confirmed by repeat observation, and follow-up searches by other observatories, including the Allen Telescope Array, found nothing at that location on subsequent nights. The most likely explanation that eventually emerged was terrestrial interference, similar to the leading explanation for BLC-1. Again, though, no single definitive source was ever pinned down with certainty. This pattern repeats throughout the field's history, often enough that researchers have a kind of unofficial rule of thumb about it. Extraordinary candidate signals tend to generate a burst of public attention within days of being reported. That's followed by a much longer, much quieter period of technical analysis. It either confirms a mundane explanation or, in the rarer cases, simply fails to reach a confident conclusion at all. The signal eventually settles into the same kind of permanent uncertainty that still surrounds the original WOW signal. It's worth understanding exactly what lies in the direction the WOW signal came from, because the location itself has fueled a great deal of speculation over the years. The signal originated from a region of sky within the constellation Sagittarius, close to, but importantly not exactly at, the direction of the galactic center, the crowded, gas-rich hub around which the entire Milky Way rotates. Early on, some researchers wondered whether the density of stars in that general direction might explain an unusually strong natural signal. There was, after all, more material along the line of sight capable of producing radio emission. But detailed follow-up work found no known star, gas, cloud, or other catalogued astronomical object sitting precisely at the coordinates the signal came from. Nothing was close enough or bright enough to obviously account for it. That absence of an obvious source is part of what has kept the case open for so long. It isn't that astronomers found something faint and unusual sitting exactly where the signal originated and simply couldn't explain its behavior. It's that when they looked at those exact coordinates, using instruments far more sensitive than Big Ear ever was, they found nothing conclusively unusual there at all. No known object was bright enough or strange enough to be an obvious culprit, artificial or natural. Whatever produced the signal, if it was a real astronomical event and not some overlooked instrumental quirk, there are three possibilities. It came from something too faint to detect through any other means. It came from something that no longer exists in the same form. Or it simply hasn't been active again during any of the windows astronomers have spent looking. Among the thousands of fast radio bursts now catalogued, a handful stand out for just how extreme their properties are. One recorded in 2022 remains. As of the most recent published analysis, the most energetic single burst ever detected. Designated FRB 20220-610A. Based on the date it was recorded, the burst was traced back to a group of merging galaxies roughly 8 billion light-years away. That means the light and radio waves reaching Earth's telescopes had been traveling for roughly 60% of the current age of the universe. In the span of under a millisecond, the source released an amount of energy roughly equivalent to what our Sun produces over the course of 30 years. All of that was compressed into a flash of radio waves, lasting a fraction of the time it takes to blink. Discoveries like this one matter for more than just the raw spectacle of the numbers involved. Fast radio bursts travel across such enormous distances, passing through so much of the diffuse, ionized gas that fills the space between galaxies. The way their signal gets subtly altered along the way gives astronomers a genuinely new tool for studying something that has otherwise been extremely difficult to measure directly: the total amount of ordinary matter spread throughout the universe. For decades, astronomers added up all the ordinary matter they could directly observe in stars, galaxies, and glowing gas clouds. The total came up noticeably short of what cosmological models predicted should exist. Astronomers had a name for the shortfall, calling it the case of the missing baryon. Baryons is the technical term for the ordinary matter that makes up stars, planets, and everything we're familiar with. as distinct from the mysterious dark matter that makes up a much larger fraction of the universe's total mass. Fast radio bursts, it turns out, are uniquely useful for solving that particular puzzle. Their signal spreads out and gets delayed slightly across different frequencies, an effect called dispersion, which directly measures the total amount of ionized matter the signal passed through on its way to Earth. That works regardless of whether that matter is glowing brightly enough to see directly through a normal telescope or not. By analyzing a large enough sample of fast radio bursts at a range of known distances, astronomers have been able to essentially weigh the normal matter of the universe using this method. The missing baryon problem has largely been resolved as a result. The matter turned out to exist in vast, extremely diffuse clouds of gas stretched between galaxies, too faint to see directly, but detectable through exactly this kind of indirect measurement. It's a genuinely remarkable outcome. A mystery that began with a single, strange, unexplained burst back in 2007, eventually turned into one of the most useful new tools in all of observational cosmology. It's entirely unrelated to any question about extraterrestrial civilizations, but arguably one of the biggest scientific payoffs to come out of this entire field so far. It's worth spending a little more time on magnetars. They've become the leading, though not fully complete, explanation for the majority of fast radio bursts. A typical star with a mass several times greater than our Sun will, at the end of its life, run out of the nuclear fuel that has been holding it up against its own gravity for millions of years. Without that outward pressure, the star's core collapses catastrophically in a matter of seconds. It crushes an object, roughly the size of a star, down to a sphere only about 12 miles across. The outer layers of the star are blasted outward in a supernova explosion, one of the most energetic events in the universe, briefly outshining an entire galaxy. The crushed core left behind becomes a neutron star, an object so dense that a single teaspoon of its material would weigh roughly the same as a large mountain here on Earth. Most neutron stars are already extraordinary objects by any ordinary standard. But a small fraction of them, somewhere around 1 in 10 based on current estimates, form with magnetic fields even more extreme than the rest. These fields are thousands of times stronger than a typical neutron star's, and these are the objects classified as magnetars. A magnetar's magnetic field is difficult to convey in any way that feels intuitive. Nothing in ordinary human experience comes remotely close. The strongest magnetic fields ever produced by human technology in specialized laboratory equipment reach only a small fraction of the strength found naturally on a magnetar's surface. At that strength, the magnetic field doesn't just surround the star. It actively distorts the physical structure of atoms anywhere near it, and it stores an almost unimaginable amount of energy within the star's crust and surrounding magnetic field. Occasionally, that stored energy gets released suddenly. Stresses build up in the magnetar's solid crust until they exceed what the material can withstand, cracking in an event astronomers call a starquake. It's similar in basic concept to an earthquake, but involving forces and energies that dwarf anything geological. These starquakes can trigger sudden, brief, extraordinarily powerful bursts of radiation. In 2020, astronomers using multiple telescopes simultaneously caught exactly this kind of event happening on a known magnetar inside our own galaxy, designated SGR 1935 + 2154. located roughly 30,000 light-years from Earth. For the first time, researchers recorded a radio burst from a magnetar with properties genuinely comparable to a fast radio burst. It arrived at almost exactly the same moment as a separate burst of X-ray radiation from the same object. That was direct, simultaneous, multi-wavelength confirmation that at least this category of event really can produce something resembling the signals seen coming from other galaxies. It remains one of the most important single observations in the entire history of this field. It moved the magnetar explanation from a plausible theoretical model to a confirmed, directly observed physical mechanism, at least for bursts of this particular scale. Breakthrough. LISTEN itself is worth understanding in more detail. It represents, by far, the largest and most well-funded search of its kind ever undertaken. It launched in 2015 with a commitment of $100 million over 10 years, funded primarily by the technology investor Yuri Milner. The project brought together researchers from some of the world's leading universities and observatories. Its explicit goal was conducting the most comprehensive, most sensitive search for technosignatures ever attempted. The project uses time on some of the largest steerable radio telescopes on the planet, including the Green Bank Telescope in West Virginia and, until its collapse in 2020, the Parkes Telescope in Australia. It dedicates hundreds of hours of observing time towards systematically surveying the 1 million stars closest to Earth, the entire plane of the Milky Way galaxy, and a sample of 100 nearby galaxies beyond our own. The sheer scale of data involved is difficult to overstate. On a single night of observation, the project's instruments can generate data volumes measured in the hundreds of terabytes. That's far more information than any team of human researchers could ever hope to review by eye. That's why the project relies heavily on automated software specifically designed to sift through that flood of data. The software compares observations of a target star against observations of nearby empty sky, and flags any signal that appears only when the telescope is pointed directly at the target. That's exactly the process that eventually surfaced BLC, one out of the Proxima Centauri data. Breakthrough Listen also made an unusual and deliberate choice early on to make its data publicly available. That allows researchers and even interested members of the public anywhere in the world to download raw observational data and run their own independent analysis. That openness has occasionally led to independent researchers spotting candidate signals the project's own automated pipeline initially missed. It adds an additional layer of scrutiny to a field where a genuine detection would be so rare and so consequential that more independent verification is generally considered a strength rather than a redundancy. As of the most recent public updates from the project, no signal examined through this effort has been confirmed as an artificial transmission from another civilization. Every candidate that has generated significant attention, BLC, one included, has ultimately been assessed as very likely explainable through conventional means. That's true even in the handful of cases, again including BLC-1, where a fully specific, confirmed, mundane source was never definitively pinned down. Part of what made the Proxima Centauri signal so compelling to the public is what we actually know about that particular star system. Beyond the technical details of the frequency and the drift pattern, Proxima Centauri is a small, dim, red dwarf star, the closest star to our own Sun at a distance of about 4.24 light-years. It's orbited by at least 2 confirmed planets. The first, discovered in 2016 and designated Proxima Centauri b, orbits its star every 11.2 days. It sits close enough to its dim, cool star that it falls within what astronomers call the habitable zone, the range of orbital distance where a planet's surface temperature could, under the right atmospheric conditions, allow liquid water to exist. The planet is estimated to have a mass somewhere around 1.17 times that of Earth. That makes it, at least in terms of raw size, one of the more Earth-like planets discovered orbiting any nearby star. That doesn't necessarily mean it's hospitable. Red dwarf stars, like Proxima Centauri, are prone to violent flare activity, sudden, dramatic increases in brightness caused by intense magnetic eruptions on the star's surface. A planet orbiting as closely as Proxima Centauri b does would be exposed to considerably more radiation during these flares than Earth ever experiences from our own, comparatively calm sun. Whether that radiation environment would be survivable for any form of life remains an open and actively studied question. So does whether it would have long since stripped away any atmosphere the planet might otherwise have held onto. Current and next-generation space telescopes are specifically designed to help answer both. A second planet in the system, Proxima Centauri c, orbits much farther out, on a roughly 5-year orbit. It sits too far from its star to fall within the habitable zone. None of this proves or disproves anything about the signal detected in 2020. But it explains, at least in part, why a signal appearing to come from that exact direction generated as much attention as it did. Proxima Centauri sits at the very top of the list of stars, close enough for a hypothetical civilization to plausibly send a detectable signal toward Earth without an enormous, unrealistic amount of transmission power. That's simply because it's so close, and because it happens to host at least one planet sitting in a zone where liquid water could, in principle, exist. Radio signals aren't the only category of evidence researchers are looking for. It's worth understanding how this search fits into a much broader effort. In 2015, astronomers studying data from the Kepler Space Telescope noticed something strange in the light curve of a star catalogued as KIC 8462852, more commonly known by the name of the researcher who first flagged it, Tabby's star. Stars normally dim only very slightly and predictably when a planet passes in front of them. That's a tiny, regular dip in brightness that repeats on a fixed schedule and rarely exceeds more than about 1 or 2% of the star's total light. Tabby's star showed dimming events that were far larger, occasionally dropping by over 20% of its total brightness. These occurred at irregular, unpredictable intervals that didn't match the signature of any known planet. The scale and irregularity of the dimming briefly led some researchers to float an idea, one hypothesis among many under serious consideration. It was a partially completed megastructure, an artificial construction built by an advanced civilization to capture energy directly from its star. The concept was first proposed theoretically decades earlier by the physicist Freeman Dyson, and is now generally referred to as a Dyson swarm or Dyson sphere. Extensive follow-up observations across multiple wavelengths of light eventually favored a far more mundane, though still genuinely interesting, explanation. The dimming was most likely caused by uneven clumps of orbiting dust, possibly the debris from a shattered comet or a collision between smaller bodies in the system, gradually passing in front of the star in irregular patterns. The dust explanation isn't universally considered fully settled by every researcher who has studied the star, but it remains, by a comfortable margin, the leading and most well-supported interpretation. Searches for technosignatures have expanded well beyond radio waves and dimming stars. They now include looking for unusual chemical signatures in the atmospheres of distant exoplanets. Chemical combinations that wouldn't be expected to persist naturally without some ongoing industrial or biological process actively replenishing them. They also include searches for laser pulses, since a sufficiently powerful and precisely aimed laser could, in principle, be detected across interstellar distances and would stand out clearly against natural starlight. None of these efforts have produced a confirmed detection, but together they represent a considerably broader, more diversified search than existed even 20 years ago. No longer relying on a single method or a single narrow slice of the radio spectrum, the search now casts a wide net across nearly every kind of physical evidence a distant technological civilization might conceivably leave behind, whether it meant to or not. There's one story from the history of fast radio bursts that deserves to be told in full. It captures exactly how strange, and occasionally how mundane, the explanation for an anomalous signal can turn out to be. For years after the original Lorimer burst was published, the Parkes Observatory in Australia kept detecting a separate category of strange, brief radio bursts. They were superficially similar to fast radio bursts in some ways, but different enough that researchers gave them their own name, calling them peritons, after a mythical creature that was said to cast the shadow of a man while having the body of a stag. Unlike fast radio bursts, which appeared to come from far outside our galaxy, the peritons showed characteristics suggesting a much closer, possibly local origin. For years, nobody could figure out what was producing them. They appeared at irregular intervals, sometimes clustering suspiciously around weekday lunch hours. That struck some researchers as an odd pattern for a natural astrophysical phenomenon to follow. In 2015, a team of researchers finally solved the mystery. The answer turned out to be almost comically down to earth. The observatory had 2 microwave ovens on site, used by staff during the day. Researchers determined that when one particular oven's door was opened before the heating cycle had fully finished, it released a brief burst of stray microwave radiation. The sensitive receiving equipment nearby was picking up that burst and recording it as an astronomical signal. The team specifically tested this scenario, deliberately opening the oven early and checking whether the telescope registered anything. The peritons appeared right on cue. The mystery had genuinely puzzled professional radio astronomers for the better part of a decade. It turned out to be explained by kitchen staff getting impatient waiting for their lunch to finish heating. That story matters here for more than just its entertainment value. It's a genuinely useful reminder of exactly how much painstaking, unglamorous investigative work goes into ruling out mundane explanations before any signal is taken seriously as a candidate for something more significant. It's part of why the field treats candidates like BLC-1 and even the WOW signal itself with the same careful, methodical scrutiny. Sensitive radio telescopes are, by design, extraordinarily good at picking up faint signals from deep space. That same sensitivity also makes them extraordinarily good at picking up ordinary, everyday sources of interference from far closer to home. Separating the two, reliably, every single time, has turned out to be one of the most persistently difficult technical challenges in the entire field. It's worth explaining, in slightly more detail, exactly how astronomers can tell that a millisecond burst of radio energy came from billions of light-years away, rather than from somewhere far closer. The method itself is one of the more elegant pieces of physics involved in this entire story. the space between stars, and especially the much larger space between galaxies, isn't a perfect, empty vacuum. It contains an extremely thin, diffuse scattering of charged particles, mostly free electrons, left over from the earliest stages of the universe and from the ongoing life cycles of stars. When a radio wave travels through that diffuse cloud of charged particles, its speed is very slightly affected. Critically, that effect is different depending on the wave's frequency. Lower frequency radio waves get slowed down very slightly, more than higher frequency radio waves, traveling through the exact same path. A burst starts out as a single, instantaneous flash across a wide range of frequencies all at once. By the time it reaches a telescope on Earth, the different frequencies within that burst will have arrived at very slightly different times, with the lowest frequencies trailing consistently behind the highest ones. That effect is called dispersion, and it accumulates gradually over distance. A burst that traveled across a short distance will show only a small amount of this frequency-dependent delay. A burst that traveled across a much larger distance, through much more of that diffuse, intervening material, will show a much larger delay. By carefully measuring exactly how much that delay is, astronomers can calculate a value called the dispersion measure. From that single number, combined with reasonable assumptions about the average density of material in space, they can estimate roughly how far the signal traveled before it reached us. This is precisely how astronomers determined that fast radio bursts, unlike ordinary pulsars from within our own galaxy, were originating from sources far outside the Milky Way. It's the same basic method used to pin down the 8 billion light-year distance of the most energetic burst ever recorded. It's also, again, exactly the kind of physical signature that makes these bursts scientifically valuable, independent of any question about their ultimate origin. The dispersion measurement itself has become one of the most effective tools available for mapping out the otherwise invisible, diffuse matter spread between galaxies. Much of the recent explosion in the number of known fast radio bursts comes from a single Canadian instrument called CHIME, short for the Canadian Hydrogen Intensity Mapping Experiment. It's a radio telescope with an unusual design, 4 large stationary half-pipe-shaped reflectors, rather than the traditional single dish that can be steered and pointed at specific targets. Because CHIME has no moving parts, it can't be aimed at a particular star the way Parkes or Green Bank can. Instead, it continuously watches an enormous swath of the northern sky at once, letting the Earth's own rotation sweep new regions of sky through its field of view every single day. Software built specifically for the task scans through that continuous stream of data in near real time, automatically flagging anything that looks like a fast radio burst. Since becoming fully operational in 2018, CHIME has utterly transformed the pace at which these bursts are discovered. In its first major published catalogue alone, the telescope detected over 500 new fast radio bursts in under a year, more than tripling the total number known at the time the catalogue was released. Subsequent catalogues have continued adding hundreds more. That kind of scale matters enormously for a field that spent its first decade working with only a small handful of confirmed detections. With a large enough sample size, astronomers can finally start doing genuine statistical analysis. They can look at how burst properties vary with distance, how many repeat versus how many appear only once, and what kinds of galaxies tend to host them. They can also ask whether different subpopulations within the overall catalogue might actually represent entirely different physical mechanisms rather than a single unified phenomenon. CHIME has also been central to identifying many of the known repeating sources. including several of the periodic ones, showing that strange, clock-like activity cycle. Its continuous, wide-field monitoring is well suited to catching a source that might only become active again, days or weeks after it was first noticed. The next generation of instruments currently being planned or built, including expanded versions of the chime design intended for the Southern Hemisphere, are expected to push the known catalogue from the current total, now numbering in the thousands, into the tens of thousands within just the next several years. That's an almost unimaginable rate of growth for a field of astronomy that didn't officially exist before 2007. There's a principle that comes up constantly in discussions of unexplained signals, one popularized by the astronomer and science communicator Carl Sagan. He framed it simply: extraordinary claims require extraordinary evidence. It's worth understanding exactly what that principle does and doesn't mean in a case like this. It doesn't mean dismissing an unusual signal outright or refusing to take it seriously. Every signal discussed in this story was taken seriously enough to generate months, sometimes years, of dedicated technical analysis by trained researchers using some of the most sensitive instruments ever built. What the principle actually demands is a specific order of operations. Before concluding that a signal represents something genuinely unprecedented, every simpler, more mundane, better supported explanation has to be tested and ruled out first, one at a time. That's true no matter how tedious or unglamorous that process turns out to be. That's exactly what happened with the peritons, eventually traced back to a microwave oven. It's what happened with the comet hypothesis for the WOW signal, seriously proposed, carefully tested, and ultimately set aside once the numbers didn't hold up. It's what happened with the HD1 64595 signal. And it's what happened, largely, with BLC1. The reason this matters isn't just abstract scientific rigor for its own sake. The history of this exact field is full of cases where an initially exciting, seemingly inexplicable signal turned out, after careful work, to have a completely ordinary source. Given that track record, any individual researcher claiming to have found definitive evidence of an artificial signal from another civilization, without first exhausting every mundane alternative, would rightly be met with enormous skepticism from the rest of the field. That skepticism has, historically, turned out to be justified far more often than not. None of this means such a discovery could never happen, or that researchers have given up looking. It means the bar for confirmation is set high on purpose. The cost of announcing a false positive to public trust, to the credibility of the entire field, and to the researchers involved personally, is considered far higher than the cost of taking a little longer to be certain. So, what would it actually take to move a candidate signal from unexplained to confirmed? Researchers in this field generally agree on a small set of criteria. None of the signals discussed tonight have satisfied all of them at once. The first is repetition. A signal that shows up once and never again is always going to be harder to confirm than one that can be observed multiple times by multiple independent teams using different equipment. Repetition allows for verification. Verification is the entire foundation of how science distinguishes a real discovery from an error or a coincidence. The second is independent confirmation. Ideally, that comes from a completely separate telescope, operated by a completely separate team, with no shared equipment or shared potential source of interference. If two observatories on opposite sides of the planet using entirely different hardware, both detect the exact same signal coming from the exact same location at the exact same time that dramatically reduces the odds that either one is picking up local interference. The third is a detailed, consistent, and specific pattern of information encoded within the signal. It would need to go beyond simply being unusual or hard to explain, and instead show structure that would be difficult to attribute to any known natural astrophysical process. None of the signals in this story have met all three of these standards simultaneously. The wow signal was never repeated, despite decades of searching. That makes independent confirmation essentially impossible with current information, however suggestive its original shape and frequency may have been. BLC-1 showed some of the right characteristics during its original observation. But similar signals later turned up when the telescope wasn't even pointed at Proxima Centauri, undermining exactly the kind of confidence independent confirmation would require. The periodic repeating fast radio bursts satisfy the repetition requirement more convincingly than almost anything else in this story. Several have now been confirmed by multiple independent observatories. But their properties, so far, remain broadly consistent with known, extreme, natural, astrophysical processes, even if the fine details aren't yet completely worked out. Until a signal manages to satisfy all three of these standards at once, the honest, professional position within the field will remain exactly where it's been for decades. Genuinely open, genuinely uncertain, and genuinely still searching. The search for radio signals is only one branch of a much larger, ongoing effort to figure out whether we're alone. It's worth understanding how that broader effort has been accelerating in recent years. The James Webb Space Telescope began science operations in 2022. It's capable of a kind of measurement earlier telescopes simply couldn't perform with any precision, analyzing the specific chemical composition of the atmospheres surrounding planets, orbiting distant stars. By studying how starlight changes as it passes through that atmosphere on its way to Earth. Certain combinations of gases, oxygen alongside methane, for example, tend not to coexist stably in a planet's atmosphere for very long without something actively replenishing them. They naturally react with each other over relatively short geological timescales. On Earth, that ongoing replenishment comes from biological processes. Finding a similar chemical imbalance on a distant world wouldn't prove the presence of life, but it would represent exactly the kind of anomaly serious enough to justify years of additional, more targeted follow-up observation. In 2023, astronomers using the James Webb Space Telescope reported a tentative detection of a molecule called dimethyl sulfide in the atmosphere of a distant exoplanet called K2-18b. On Earth, that compound is produced almost exclusively by living organisms, primarily marine phytoplankton. The detection generated significant excitement and equally significant caution. The measurement sat right at the edge of what the telescope could reliably distinguish from background noise. A follow-up analysis in 2025, using a different instrument on the same telescope, reported additional evidence for the same molecule. That only intensified the debate. Since then, several independent teams have gone back through the same raw data using their own separate analysis methods. Most of them have not been able to reproduce the signal with any real confidence. At least one NASA-led reanalysis found no conclusive evidence for the molecule at all. The case isn't fully closed, but the balance of evidence has shifted considerably since the original announcement, away from a confirmed detection and toward the more likely explanation that the signal was an artifact of noise and instrumental limitations, rather than a genuine chemical signature. What's changed dramatically over just the past several years is the sheer number of these open cases accumulating at once. Unexplained radio bursts, ambiguous atmospheric chemistry, unusual stellar dimming patterns, each one individually inconclusive. Together, they represent a research landscape that looks nothing like it did even a decade ago, when a single strange signal could dominate the conversation for years simply because there was so little else being actively investigated alongside it. The search for artificial signals hasn't always enjoyed the steady, well-funded support it has today. Its political history is worth understanding, because it explains why so much of this research has ended up funded privately rather than through government space agencies. NASA ran its own formal SETI program, starting in the late 1980s, called the High Resolution Microwave Survey. It was designed to systematically scan the sky using some of the largest radio telescopes available, combining a targeted search of nearby stars with a broader all-sky survey. The program launched in October of 1992, on the 500th anniversary of Christopher Columbus's arrival in the Americas. That timing was a deliberate symbolic choice, meant to frame the effort as a new kind of exploration. It lasted less than a year. In 1993, facing budget pressure and a broader push in Congress to eliminate spending seen as speculative or unlikely to produce practical results, the United States Senate voted to eliminate all federal funding for the project. Critics specifically mocked the search for alien signals as an unproductive use of taxpayer money. Researchers in the field sometimes refer to that sentiment, half bitterly, as the giggle factor. The tendency for this particular area of legitimate scientific research to be dismissed reflexively as science fiction, rather than evaluated on its actual merits. That defunding effectively ended government-supported SETI research in the United States for the following decades. The search didn't stop, but it shifted almost entirely toward private philanthropic funding and university research budgets. That's a significant part of why an organization like Breakthrough Listen, funded by a private individual rather than a government agency, has become the dominant force in the field today. In more recent years, that political climate has shifted somewhat. NASA has, since 2021, begun funding smaller-scale technosignature research once again. Through competitive research grants distributed to individual universities and research teams. Still, nothing on the scale of a dedicated, centrally funded program comparable to what existed briefly in the early 1990s. The broader search for life beyond Earth, focused on biosignatures rather than technosignatures specifically, has fared considerably better in terms of consistent government funding. Biosignatures mean chemical evidence of any life at all, rather than evidence of technology. That's part of why missions like the James Webb Space Telescope, built primarily for general astrophysics, have nonetheless become such valuable tools for this particular question, as a secondary benefit of their broader capabilities. Any honest account of this search has to reckon with the loss of Arecibo Observatory. For over half a century, it was one of the single most important instruments this entire field ever had access to. Completed in 1963, built into a natural limestone sinkhole in the hills of Puerto Rico, Arecibo's main reflector dish spanned 1,000 feet across. It was, for decades, the largest single-aperture radio telescope on the planet, a record it held until a larger instrument was completed in China in the 2010s. Arecibo's role in this story runs throughout nearly every chapter of it. It transmitted the 1974 message toward Messier 13. It carried out repeated follow-up searches of the coordinates the WOW signal came from. It was the instrument that first identified the repeating fast radio burst designated FRB 121102 in 2016. That was the discovery that ruled out purely catastrophic, one-time explanations for that entire category of signal. By the 2010s, decades of tropical humidity, hurricane damage, and deferred maintenance funding had left the massive structure increasingly fragile. In August of 2020, one of the steel cables supporting the enormous receiving platform suspended above the dish snapped without warning, tearing a gash through the reflector below. Engineers began assessing repair options. But before those repairs could begin, a second, larger supporting cable failed in early November of that same year. The structure's remaining cables were now judged too unstable to safely support repair crews, and the risk of a sudden, uncontrolled collapse was considered too high. The decision was made to decommission the telescope rather than attempt further repairs. On December 1st, 2020, the remaining cables gave way entirely. The 800-ton receiving platform crashed down into the dish below. It destroyed, in a matter of seconds, an instrument that had taken years to build and had spent nearly 6 decades as one of the most productive tools in the history of radio astronomy. Its loss left a genuine gap in the field's overall observing capacity. Newer instruments like the expanding CHIME network and the still under construction square-kilometer array are gradually working to fill that gap. But nothing has yet fully replaced Arecibo's specific combination of raw collecting area and geographic location. Modern radio astronomy, including this specific search, now faces a genuinely new challenge that didn't exist in anything like its current form even a decade ago. It's the rapid growth of large satellite constellations providing global internet access from low Earth orbit. Companies operating these networks have launched and continue to launch thousands of individual satellites. Each one broadcasts radio signals back down toward Earth as part of normal operation. Each one represents a moving, orbiting source of exactly the kind of radio emission a ground-based telescope has to work extremely hard to filter out from genuine astronomical signals. A fixed ground-based transmitter has a position and frequency that can be well documented and filtered out consistently. Thousands of satellites moving rapidly across the sky at different altitudes and orbital paths present a constantly shifting source of potential interference, one that grows more complicated with every new batch of satellites launched. Radio astronomers have raised increasingly urgent concerns about this trend throughout the 2020s. Some observatories have documented specific instances where satellite transmissions have directly interfered with sensitive observations, occasionally producing brief signals in recorded data that require careful additional analysis to distinguish from genuine astronomical sources. This adds a meaningful new layer of difficulty to exactly the kind of work this story has been describing. Every candidate signal identified going forward has to be checked not just against known ground-based interference and known aircraft and known older satellites. It also has to be checked against a rapidly expanding, constantly changing population of newer satellites, numbering in the thousands and continuing to grow. Researchers and telescope operators have been working directly with satellite operators to establish coordination protocols, including scheduled quiet periods and improved satellite transmission designs, intended to minimize interference with sensitive radio astronomy frequencies. But the underlying tension between an increasingly crowded orbital environment and the increasingly sensitive instruments trying to listen past it isn't going away. It's likely to remain one of the defining practical challenges for this entire field over the coming decade. It's worth putting the actual scale of this search into honest perspective. It directly explains why the absence of a confirmed detection, so far, says relatively little on its own about whether anything is actually out there to find. The Milky Way alone contains somewhere in the range of 100 billion to 400 billion stars. Breakthrough Listen's flagship survey, by far the largest systematic search conducted to date, has examined roughly 1 million of them in any real detail. Even in the most generous framing of that number, it represents a tiny fraction of 1% of the stars in our own galaxy alone. And that's before accounting for the fact that most of those observations covered only a limited range of frequencies, for a limited duration, at a single moment in time, rather than continuously monitoring each star for years on end. A useful way some researchers in the field describe this problem is to imagine trying to determine whether the ocean contains fish by dipping a single drinking glass into the water, at one spot, for one brief moment. Coming up empty tells you remarkably little about what the rest of the ocean actually contains. That framing isn't meant to suggest the search has been pointless, or that a positive detection is somehow likely simply because so little ground has been covered. It's meant to explain, honestly, why researchers in this field are careful never to treat the absence of a confirmed signal as strong evidence that nothing is out there. By the same logic, a handful of genuinely strange, unexplained candidate signals shouldn't be treated as strong evidence that something definitely is. Both conclusions would be reaching well past what the actual data currently supports. What the data supports is considerably more modest and considerably more interesting. It's a search still in its early stages, using tools that have improved by orders of magnitude just within the working lifetime of many of the researchers still actively involved. Along the way, it keeps uncovering an ever-growing catalogue of strange, extreme, and occasionally still unexplained phenomena, regardless of how the central question of the search itself ultimately gets answered. It's worth understanding exactly what the next generation of instruments will actually be capable of. The leap in sensitivity involved is genuinely difficult to overstate. The square-kilometre array is currently under construction across sites in South Africa and Western Australia. It's being built in phases, with the first phase already assembling thousands of individual antennas designed to work together as a single, enormous, distributed telescope. The core idea behind this kind of design is called an interferometer. Combining signals from many smaller antennas spread across a wide area can, with the right processing, achieve a level of resolution and sensitivity that would otherwise require building a single, physically impossible dish large enough to match the combined collecting area of the whole array. Once the full array is complete, its total collecting area will be roughly equivalent to 1 square kilometre, dramatically larger than any single existing radio telescope. The resulting increase in sensitivity means it will be capable of detecting signals many times fainter than current instruments can pick up, across a correspondingly much larger volume of surrounding space. For a search built around trying to catch a rare, brief, or extremely faint signal, that kind of sensitivity increase doesn't just mean modest incremental progress. It effectively multiplies the total number of stars and the total range of distances that can be meaningfully searched in a given amount of observing time. A separate project, the Next Generation Very Large Array, is planned for construction across sites in the United States. It aims to replace and dramatically expand upon the current Very Large Array in New Mexico, with similarly ambitious goals for both general astrophysics and, as a direct secondary benefit, technosignature research. Researchers involved in Breakthrough Listen and similar efforts have already begun planning how they'll make use of these new instruments once they come fully online over the coming years. There's a reasonable expectation within the field that the total volume of sky and the total number of individual stars meaningfully searched for artificial signals will increase by a significant factor within roughly the next decade, compared to everything accomplished across the entire history of the search up to this point combined. Whether that dramatically expanded search eventually turns up something conclusive, or simply continues adding to the growing catalogue of strange, ultimately explainable phenomena, either outcome would represent genuine scientific progress. Either outcome is, by design, exactly what these new instruments are being built to help determine. Behind every signal in this story is a smaller, quieter story about the people who actually did the work of investigating it. That part of the story rarely makes it into the headlines. Jerry Amon, the astronomer who circled the WOW signal in red ink back in 1977, spent years afterward fielding questions about it. He remained, for the rest of his life, notably cautious in how he described it publicly. He consistently pointed out that a single, unrepeated data point, however striking, could never be enough on its own to draw a firm conclusion either way. He continued working as a volunteer on the Big Ear project for years afterward, reviewing countless additional printouts that never produced anything remotely comparable. That's a level of patient, largely unrewarded persistence that runs through nearly every career in this field. The team that eventually solved the Periton mystery, tracing years of unexplained signals back to an impatiently opened microwave oven, spent a significant amount of time methodically testing and eliminating far more exotic hypotheses first. That's simply what the process requires, regardless of how anticlimactic the eventual answer turns out to be. The researchers who identified BLC spent months afterward carefully working through the more mundane explanations before the story ever became public. They've spoken candidly since about how differently the story unfolded once news of the signal leaked to the press ahead of their own analysis being finished. Public excitement raced well ahead of the far slower, more careful process of actually figuring out what the signal was. That gap between how quickly a strange signal can capture public attention and how slowly the actual science behind it has to move in order to be trustworthy is probably the single most consistent thread running through this entire story. It runs from 1977 all the way through to whatever candidate signal eventually gets flagged next. None of these researchers are chasing a headline. Almost all of them, when asked directly, will tell you they consider the far more mundane explanation, the most likely outcome for practically any new candidate signal that comes across their desk. They'd tell you that even while still spending the following months carefully, rigorously, checking to make sure. That combination, deep skepticism paired with genuine sustained effort, is a harder balance to strike than it sounds. It's the actual engine behind everything described tonight. Not dramatic certainty in either direction, but a slow, careful, decades-long habit of looking closely at things that don't immediately make sense. It means refusing to stop looking until there's a real answer, or at least until every easier answer has been properly ruled out. There's an entire, separate, and genuinely contentious debate running alongside this search. It's over whether humanity should be listening at all, or whether we should also be actively transmitting, deliberately announcing our presence to whoever might be listening back. That practice has its own name, distinct from SETI, called METI, short for Messaging Extraterrestrial Intelligence. It has generated real disagreement, even among researchers who otherwise fully support the broader search for signals. In 2017, a team of researchers transmitted a structured, deliberately composed radio message toward a red dwarf star called GJ273, using a radio telescope in Norway. The star sits about 12 light-years away and is known to host at least one planet within its habitable zone. The message, sent in multiple parts over the following months, encoded basic mathematical and scientific concepts, along with a short musical composition. It was specifically designed to be interpretable using logic alone, without relying on any shared language. Given the distance involved, any response, if one were ever sent back immediately upon receipt, couldn't possibly reach Earth for at least 24 years. The decision to send that message, and similar messages sent by other teams over the years, has drawn sharp criticism from a number of prominent scientists, including the physicist Stephen Hawking. He argued publicly, on more than one occasion, that deliberately broadcasting our location and capabilities to unknown civilizations carried genuine, difficult-to-assess risk. He drew a comparison to the historical record of what has often happened on Earth when a technologically less advanced society made first contact with a more advanced one. Others in the field have pushed back on that framing. They argue that Earth has already been unintentionally broadcasting radio and television signals into space for close to a century. Any civilization already capable of detecting a deliberate, targeted transmission would very likely already be capable of detecting our accidental leakage anyway, making the additional risk from a deliberate message comparatively small. There's no scientific consensus on this question. There's also no single governing body with the authority to make a binding decision on humanity's behalf about whether or how to respond if a genuine signal were ever confirmed. That gap has itself become a subject of ongoing discussion within the field. Some researchers and organizations are calling for the establishment of clearer international protocols, agreed upon in advance, for how the global scientific community should verify a candidate's signal, communicate about it publicly, and decide collectively whether or how to respond. That's precisely so. Those decisions aren't left to whichever individual team or individual telescope happens to be the first to notice something. For now, that framework remains informal at best, built more on academic tradition and mutual professional trust than on any binding agreement. Whenever the next genuinely compelling candidate signal does turn up, however it eventually gets explained, the scientific community will likely be navigating two questions at once. Not just the technical question of what it actually is, but the far less settled question of what, if anything, ought to be done about it. There's one more technical detail worth understanding. It explains exactly why researchers get genuinely excited about a signal like BLC, one in the first place, beyond simply its direction or its timing. It comes down to bandwidth, meaning how narrow or how wide a range of frequencies a given signal actually occupies. Almost every natural astrophysical process that produces radio waves, whether it's a star, a gas cloud, a pulsar, or a magnetar, tends to do so across a relatively broad range of frequencies at once. The physical processes generating that radiation, thermal emission, synchrotron radiation from charged particles spiraling through magnetic fields, and similar mechanisms, simply don't naturally concentrate their energy into an extremely narrow slice of the radio spectrum. A genuinely narrowband signal is one confined to an extremely small range of frequencies, something on the order of a single hertz out of a spectrum, spanning many megahertz. As far as known physics is concerned, that's something nature essentially doesn't produce on its own. Human technology, on the other hand, produces narrowband signals constantly and deliberately. Concentrating a transmission's energy into a narrow, specific frequency is exactly what makes radio, television, and communication technology work efficiently in the first place. This is precisely why SETI researchers have, for decades, treated narrowband signals as one of the single most promising categories of evidence to search for. Any other technological civilization, regardless of how different its specific engineering might look from ours, would likely run into the same basic physics and might arrive at similarly narrowband transmissions for similarly practical reasons. BLC once stood out specifically because it was narrowband, sitting in an extremely tight frequency range. That's exactly the kind of signature that doesn't have an easy, natural explanation, which is a significant part of why it triggered so much serious attention from the research team in the first place, rather than being dismissed immediately. It's also, notably, exactly the kind of signature that's easiest to accidentally produce with ordinary human electronics. Almost every piece of consumer and industrial equipment on Earth, computers, cell phones, medical equipment, vehicle electronics, generates its own narrowband radio emissions as an unintentional side effect of normal operation. That dual nature, narrowband signals being simultaneously the most theoretically compelling evidence of alien technology and the most practically common form of accidental terrestrial interference, is precisely what makes a case like BLC one so difficult to resolve definitively. The very property that makes a signal exciting is the same property that makes it easy to confuse with a piece of nearby electronics accidentally leaking into the same frequency range. Untangling those two possibilities definitively for any given individual signal remains one of the genuinely hardest, most labor-intensive parts of this entire search. Put all of these pieces together, and a clearer picture starts to emerge of what this search actually looks like from the inside, far removed from how it usually gets portrayed in headlines. It isn't one dramatic discovery waiting to happen. It's a slow, cumulative, decades-long process of building better instruments, catching stranger signals, and patiently working through the layers of possible explanation for each one. Natural astrophysics first, terrestrial interference second, and only after both of those have been exhausted, anything else. Most signals get explained. The peritons turned out to be a microwave oven. The comet hypothesis for the WOW signal didn't survive contact with the actual physics. HD1 64595 turned out to be almost certainly local interference. Most fast radio bursts now trace back convincingly to magnetars and other extreme but entirely natural stellar remnants. But not every signal gets fully explained. That residual category, small, carefully documented, and revisited whenever better data becomes available, is where this entire story actually lives. The WOW signal sits there. BLC, one sits there too, in a slightly different way, probable but not proven. Some of the periodic repeating fast radio bursts sit there as well, broadly consistent with known physics, but not yet fully, specifically accounted for down to the last detail. None of that amounts to proof of anything beyond what it plainly is, a genuinely unresolved set of open questions, sitting inside one of the most careful, most heavily scrutinized areas of modern astronomy. But it also isn't nothing. Each of these cases represents a real signal recorded by real instruments, examined by real scientists who spent real time trying, and so far failing, to fit it neatly into what we already understand. That's the actual, honest shape of this mystery. Not a confirmed answer in either direction, but a growing, carefully maintained list of things the universe has shown us that we still can't fully explain. It stays open specifically because closing it prematurely, in either direction, would mean pretending to know something nobody currently does. The wow signal is still sitting there, unexplained, in an old printout with 3 red letters scrawled in the margin, more than 4 decades after it happened. BLC1 is still filed as a probable, but not confirmed, case of interference, the specific source never actually identified. And somewhere out among the fast radio bursts still being catalogued every month, there are patterns scientists can describe in exhaustive technical detail and still can't fully explain. That's not a flaw in the science. That's what science looks like while it's still actively happening, before the story gets simplified down into a tidy answer for a textbook. Real research is slower than that, messier than that, and far more honest than that. Thank you for spending tonight with me exploring some of the strangest, most carefully studied, and still genuinely unresolved signals ever picked up from space. If you found this as fascinating as I did, take a moment to like this video and subscribe to the channel. It genuinely helps this kind of careful, patient storytelling reach more people who are curious about the universe the way you are. And the next time you're outside on a clear night, looking up at a sky full of stars, remember that somewhere out there, radio telescopes are listening, right now, to frequencies human eyes will never see. They're quietly recording data that might, someday, years from now, turn out to contain the answer to one of the oldest questions we've ever asked. Whether anyone else out there is listening back, good night.